and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Jason Schwartz.
Thank you, William, and thank you everyone for joining us today. I'm here to make the case for cyclic nucleation cleaning. So it's also called CNP cleaning. It's a new cleaning technology that's come out in the last couple of years, and there's a few equipment manufacturers that have started to make it. And I wanted to talk a little bit about what it does and why it's so great. So it goes by several names. CNP, which stands for Cyclic Nucleation Process, VCN, Vacuum Cyclic Nucleation, or pressure pulse, depending on which machine manufacturer you're talking to. But they're all talking about the same thing. And the key features here are that you've got a machine that uses a vacuum pump to vary the pressure of a cleaning system, specifically in the work chamber. So some of these vacuum systems are already out on the market, but they pull a stable vacuum. This is where the cyclic part of this comes in. You're varying the pressure, kind of cycling it between low and atmospheric pressure. And this low pressure, especially in an aqueous system, creates a phase change in the cleaning solution, right? So you're forming air bubbles. You're essentially boiling the cleaning solution at a much lower temperature, and these air bubbles form and implode on the surface of the part, which is really cool. And this creates several different cleaning effects that are unique and really effective when it comes to certain applications. So, as we talked about, the CNP process changes the pressure of the system. And I know this is a bit of an old school phase diagram here, but we'll walk through it. It's pretty simple to understand, I promise. All right. So if you look here at this middle dotted line, the 100 to 100, that's the normal boiling point of water. Everybody knows, you put a pot on the stove, and when that temperature hits 100 degrees C or 212 degrees Fahrenheit, the water starts to boil. And what this chart is showing us is that as you lower the pressure, so atmospheric pressure in this case is 101 kilopascals, but as you lower the pressure, you're actually lowering the boiling point. So the boiling point will stay on that line where that 100 degrees C and 101 kPa meet. And as you lower the pressure from 100 to say 20, right, the temperature that water boils is going to lower along that line. And so what we found in the CNP process is most of these machines are able to get down consistently to about 20% of atmospheric pressure in the work chamber. On the drying stages, they can get actually even lower than that, but a good comfortable number is 20% of atmospheric pressure. That lowers the boiling point of water from 100 degrees C to about 50, 55 degrees C. Ballpark numbers. And so what's really cool is if you heat the solution up above 55 degrees C, it's going to start to boil. So when it boils, we're creating these air bubbles, right? We're creating water vapor inside of your cleaning tank. The cool thing is we already know how these air bubbles work. The bubble formation and the cleaning action is very similar to ultrasonics, right? So ultrasonics work the same way. We've used ultrasonics in cleaning for years. You have this bubble that grows with vapor inside of it, and then it collapses on itself and puts kind of this fluid jet towards the surface of the part. And that creates a really powerful cleaning effect. But unlike ultrasonics, the cool thing about CNP processes is the bubbles actually form on these nucleation sites. That's where this N, the nucleation, comes from. So what is a nucleation site? Well, it's basically any surface where the bubble can start forming. So again, going back to our water boiling in a pot, you already see this happening every day. You look at the water starting to boil here, you can see those bubbles are forming all around the bottom of that pot, all around the edge on the metal surface of it. Those are the nucleation sites. The same thing is happening in this CNP process. Now, why is that important? Is unlike ultrasonics, which shoot these bubbles out and create them through sound waves and cavitation, the nucleation sites are on these surfaces that include the wash chamber walls, just like your pot, the basket or fixture that you're using. But what's really cool, it's also directly on the part surface, right? If you've got a metal part that goes into this chamber, you're going to have a nucleation site on the surface. The other place you're going to have a nucleation site is on particles. And that's really cool because now you've got cleaning action forming and going on right where the thing that you're trying to remove is. You don't have to direct it towards your soil, your particle that you're trying to remove. It automatically forms around that particle. So that becomes really, really interesting when you have particles that are in difficult to reach areas, right? So here, this little yellow blob is representing a particle, and that particle is kind of latched into a blind hole. So normally that's a pretty difficult area to clean because you have to get fluid into the blind hole and try to flush that particle out. But with the CNP process, you're forming bubbles on the surface. You're forming bubbles in actually multiple places, right? One is right on that particle. So you're going to get that bubble forming around that particle, as you can see on the left, and then it's going to implode out and shoot that particle away. But you're also going to get air bubbles forming at the bottom of that blind hole. And as those bubbles expand, as you can see in the diagram, it's going to push fluid and the particle out of the hole. So by forming in these really unique places compared to our normal cleaning processes, CNP can be really effective in complex geometries. And we can see this a little bit easier as well in the next slide here. A lot of times you may not have a blind hole, but you've got this kind of crevice where you can't see what's going on. You've got a kind of a hole and a turn, whether that's a 90-degree or if you've got some type of heat exchanger where you're looping around inside. That's really hard to flush out. It's really hard to reach. With ultrasonics, it's really hard to flush fluid through because every time you hit that 90-degree turn, you lose all of your mechanical energy. But with the CNP, again, because we're forming these bubbles inside of whatever cavity or tube that you're doing, you're pushing particles out and away, and you're pushing fluid out. The other thing that's really cool about the CNP process is when you push this fluid out, remember, we're not just doing this once, but we're cycling the pressure. So we've pushed the fluid out, then we've returned to atmospheric pressure, and the whole thing collapses back into itself. That means you're going to push the fluid out and then push it back into the space. That's called asymmetric flow. You're not flowing in one direction. And that really helps bring fresh cleaning solution into these tight to reach spaces. So, and kind of like we talked about, the bubbles are the same as ultrasonics in the fact that they, implode on themselves and create this jet. But as you can see on the ultrasonic picture to the right, you have to direct the ultrasonics at the part. So if you look on the bottom right, those ultrasonics are pointing towards the surface of that part. They're never going to be able to go and reach up and around into that cavity to get to those bubbles. Whereas in a CNP process, the bubbles form right where the soil is. And it's really excellent for complex geometries in that respect. It's also less powerful than ultrasonics. So sometimes the things that happens with ultrasonics, if you use too low of a frequency, too powerful of an ultrasonic, you can create some metal damage on the part. The CNP is a lot gentler and a lot more directed directly at those particles. So what are the process considerations with the CNP, right? Well, as we talked about, we're lowering the boiling point of water to 50, 55 degrees C, which is about 130 F, right? So you really need temperature above that 130 F. If you have a cleaning solution at room temperature, even if we drop that down to drop the boiling point down to 50 degrees C. If you're sitting at 25, you're not going to get any of the CNP action. So you need some heat in there to help induce that phase change. You can actually use CNP in a machine with ultrasonics, spray under immersion, spraying, as long as you've got the right work chamber. and you can do these processes one after another. In some cases, you can do them in tandem. You can actually run ultrasonics while you're running CMP. And one of the cool things is it actually increases the power of the ultrasonics because it degasses the solution so quickly. So since you're under vacuum, you're pulling all of that air out. You're pulling all of the entrapped air in the solution out. That increases the power of the ultrasonics. But like we just talked about, it also increases the chance that your ultrasonics are going to damage your metal parts. So you've got to tone down the ultrasonics if you use it in tandem with CMP. But it's great that you can do both processes in one chamber. The last thing to talk about is there's lots of foam, right? We are creating by just the process itself tons of little air bubbles in solution. Those little air bubbles exacerbate foam, they cause foam. If you have some type of cleaning solution there that can foam, it will foam in a CNP process because you are, again, creating air bubbles. It's the whole point of the CNP. So you get lots of foam. You've got to work with a cleaning equipment supplier and a cleaning chemical supplier to find the right match, right? So that you get a product that won't foam in the process. So what is it good for, right? We talked a little about the complex geometries. Anywhere where you've got an area that you need to clean that's really hard to access, CNP is great for that type of cleaning. Additive manufactured metal parts, it's great for this. We'll get into that a little bit more in a minute, but they usually have a lot of really fine particles. And if you need to get rid of those particles, CNP is a great way to do that. And tubes with a high aspect ratio. So what's a high aspect ratio? If you look on the right, we've got a tube or a cooling channel here built into this heat exchanger where you've got a very small orifice, a very small in and out, but a very long tube. So it's the length of your tube divided by the diameter of the entryway. That's your aspect ratio. So this is very long with a very narrow opening. CNP is great for whenever you have something like that. And then the bends and the curves within this tube actually help it even more. So when we're talking about metal parts in the additive manufacturing space, one of the reasons CNP is so good is you've got this particulate removal problem, right? You've got all this metal powder that you're forming these really cool complex parts with. And so you don't have a lot of normal stuff that we see in the cleaning world. You don't have a lot of oils and coolants. You don't have, because you're not machining the part yet, but you've got this powder. And this powder, when it gets into these really tight spaces, can be really hard to remove. So how do you do that? Because you can't dissolve the powder because that's what the part is made of. That's when the CNP comes in. So if you look on the bottom, we've got some medical implants here. And one of the cool things that the additive process does is you can create this really rough, complex surface that helps that implant fuse into the bone better. Well, that's great because that rough surface can only be achieved with the additive process, or it's much easier to achieve at least. But the downside to additive is the really tiny metal particles your bone treats as foreign objects, or not your bone, your body. So it actually thinks that those are bacteria or something that shouldn't be there, and you have this immune reaction to those tiny, tiny particles. So you have to get them 100% clean. You have to get 100% particle removal. That's really difficult with traditional cleaning methods. But because the CNP forms these bubbles around the surface of the part, it becomes really good for this type of application. So that's one example of where CNP is great. I hope you guys have enjoyed it. We've got a couple of frequently asked questions that I will go through. So often one of the things that comes up is how do you remove the soils so that they don't redeposit on the parts? And that's a great question. And that comes down to filtration. That's the same thing we've figured out many times over the regular cleaning process is working with your equipment supplier to match your filtration, the filter size to your particle size so that you actually need it a little bit less so that those particles can't get through. going through the different types, bag filters, whether you need a cartridge filter, kind of dialing in that process is really important not to get redeposition. What other industries or applications can this be used for? This can be used for any application or industry where cleaning particulate or having really good surface cleanliness is paramount, right? So that includes some aerospace parts. We talked about medical, heat exchangers, complex geometry, but the other really interesting applications are for the semiconductor industry. So when you're talking about not just building wafers, but building the machines that cut the wafers, that make the advanced packages, they have to go into these ultra clean rooms, and cleanliness is paramount there. So cleaning the parts that build those machines has been a great application for this because you get the best surface cleanliness with this process. The optics industry is another one where you're talking about surface cleanliness being paramount. It's been really good and effective in the optics industry. Other than additively manufactured parts, what type of parts can this be used for? We kind of talked about this a little bit, the variety of industries. We've done this on anything with a complex geometry. We've done this in remanufacturing applications where you've got a engine turbo that has these complex interior channels and carbon smut in there, and getting cleaning solution to those interior channels effectively has been great for this particular application. So that has been what I've got, and I really appreciate everybody's time. I hope you enjoyed it, and I'll turn it back over to you, William.
Thanks, Jason. Thank you guys for watching this Tech to Tech session. If you'd like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@kyzen.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.